Heat really is the wrong word there. It's really enthalpy. It's enthalpies that you're adding or subtracting, not heat. But the name of the law remains. It's called Hess's law of heat summation, or Hess's law for short. And Hess's law, to put it into words, gives us a couple of new vocabulary terms. T, V, one way of stating it. There are several equivalent ways, but one way of stating it is the standard enthalpy change for some reaction is equal to the sum of the standard enthalpy changes the standard enthalpy change for some reaction is equal to the sum of the standard enthalpy changes of the reactions which add to make the one of interest. It's not exactly the statement in the book, but it says the same thing. And it's probably not the one you learned in freshman chemistry, but it's equivalent to that one too. Actually, the one you learned in freshman chemistry is a subset of this one. But there's some new terminology there. What the devil does standard mean? Refers to what's known as the standard state. That's the one that doesn't have these words beings. Standard state refers to pure substances at a pressure of 1 bar, period. End of definition. Until we get into solutions and stuff in solution, then we need some other terms there. But now we're dealing with pure substances, pressure is 1 bar. There is no standard temperature. It's important to remember, important to know that. There is no standard temperature. Now, to compare data, we always need to use the same temperature or our data will not be the same. So we need to specify a temperature for comparison purposes, but the specification of temperature is not part of the standard state. Chemists use a temperature of 298.15 Kelvin, which equals 25 degrees Celsius, which is in essence room temperature. Slightly higher than we typically keep our room temperatures, but it's a nice round number, at least in a counting scheme of 5s. Biochemists and biologists use a bizarre number, 310 Kelvin, 37 degrees Celsius. Why in the dickens do they do that?
That's internal temperature of the body.
Of what body?
Humans?
Is all biology at that temperature?
No.
Then why do biologists use that temperature?
Because we're conceited.
How can you compare a plant to a human body?
Just the human body is usually the system of interest.
For whatever reason, the body temperature is used as the reference temperature in biology and biochemistry. It works if you're dealing with medicine. It makes no real sense if you're dealing with any organism other than humans. But they do that change nonetheless. Some geologists, particularly those known as mineralogists, that look at how minerals crystallize, usually from molten rock deep within the earth, use a reference temperature of 1500 Kelvin. Very, very high temperature, and it's still well below the melting point of many rocks. But it's a much, much higher temperature because that's fairly typical of the temperatures at which minerals really crystallize. At least those that crystallize from molten rock. Some crystallize out of water. Different temperature, different reference temperatures for different purposes. There is no single standard temperature. That said, we are chemists. Every piece of data in our textbook, in that table at the back and so forth, is referenced to 298 Kelvin. And you'll find that being true pretty much repeatedly for chemists, except biochemists. We denote standard state when we're talking about enthalpies. The standard enthalpy change, a change in the enthalpy standard state. The superscript 0 bar, it's called a 0 bar, mean standard state, where the pressure is 1 bar. The old-fashioned standard, where the pressure was 1 atmosphere, used the superscript 0, but the atmosphere was thrown out as standard pressure in November of 1961. Let's see, it's about 50 years ago, isn't it? Yet freshman chemists, 3 books, still use atmospheres when we should be using bar. Change in the enthalpy under standard conditions. Standard conditions mean pure materials, pure reactants and products at a pressure of 1 bar. 1 bar is approximately 1